What if I told you there's a new kind of computer being built right now? One that, well, it doesn't really play by the rules we're used to. Instead, it runs on the weird, mind-bending laws of the universe itself. This isn't some far-off sci-fi dream, it's happening, and it's called quantum computing.
And the stakes here? They're huge. Just think about what that means. We're talking about a machine that could literally design new drugs by simulating molecules one by one. This isn't just about making our computers faster. No, this is about solving problems that are, right now, completely impossible for even the most powerful supercomputers on the planet.
Okay, so how is any of this even possible? Well, to get it, we've got to go all the way back to square one. We need to completely rethink the most basic building block of information that we've used for decades, the bit. We're about to enter a world that's way beyond just a simple on or off.
And this is where we meet the star of the show, the quantum bit, or as everyone calls it, the qubit. Now, it's super important to get this straight. A qubit is not just a faster, beefed-up version of a regular bit. It's something else entirely, a whole different kind of information, born from the strange world of quantum physics.
So let's break down the difference, because it's a big one. Think about a normal computer bit. It's basically a light switch, right? It's either on, which is a 1, or it's off, a 0. That's it. Simple. But a qubit, oh, it's more like a spinning coin. While that coin is flipping through the air, it's not heads or tails. It's kind of both at the same time. It's in this weird state of pure possibility, a mix of 1 and 0 all at once.
And this mind-blowing ability to be both a 1 and a 0 at the exact same time, it actually has a name. It's called superposition. It's this core idea that a qubit can just hang out in a combination of all its possible states. The really weird part, it only picks a side. It only collapses into a definite 0 or 1 the instant we look at it, the moment we try to measure it. Here's a cool way to think about it. You see this old toy? It's called a thaumatrope. On one side, you've got a bird. On the other, a cage. Two separate things. But what happens when you spin it really fast? Your brain kind of blurs them together, and suddenly you see the bird inside the cage. You're seeing both images at once, as one thing. And that's a fantastic real-world way to picture what superposition is like.
But wait, superposition is really only part one of the magic trick. The real power, the thing that unlocks the massive potential of a quantum computer, happens when we link these qubits together. And we do that using another totally bizarre quantum effect, a connection so strange it was called spooky.
So let me ask you this. Go back to that spinning coin idea. What if you could take two of those coins, link them in some way, and then send them to opposite ends of the galaxy? And what if, the very instant you looked at one and it landed on heads, you knew instantly that the other one, light years away, had to be tails?
I mean, it sounds impossible, right? It was so out there that even the great Albert Einstein just couldn't get his head around it. He famously called it spooky action at a distance. For him, the big problem was that it seemed like information was traveling faster than the speed of light, which, well, that was supposed to be the ultimate speed limit of the universe.
But here's the thing. It turns out Einstein was wrong on this one. This spooky action is absolutely real, and it's called entanglement. When you entangle two qubits, they're no longer separate things. They become a single unified system. So whatever happens to one instantly influences the other. Doesn't matter if they're a nanometer apart or on opposite sides of the universe.
Okay, so now let's put the two pieces together. You take superposition, where each qubit is both a 1 and a 0, and you combine it with entanglement, where all the qubits are linked together. What you get is, well, it's a straight-up explosion in computing power. We're not talking about a small improvement here. This is a massive, exponential leap.
Just look at these numbers for a second. If you have 20 regular bits, you can represent one number at a time. That's it. But with just 20 qubits, because they're all in superposition and all entangled, they can represent every single possible combination of those 20 positions all at the same time. That's 2 to the power of 20. And how big is that number? It's over a million. 1,048,576 to be exact. So, with just 20 tiny qubits, you can explore a solution space with over a million possibilities at once. And get this, every time you add just one more qubit, you double that power. That's what people mean when they talk about quantum advantage.
All right, so if these things are so powerful, why don't we all have one? Why isn't there a quantum laptop on my desk? Well, it turns out that building these things, it's really, really hard. Harnessing the quantum world is one of the biggest scientific and engineering challenges we've ever faced.
But the promise, man, the promise is huge. Think about it. We could create brand new medicines because simulating a molecule is a quantum problem at its heart, and these machines are built for that. We could design incredible new materials, literally from the atom up. We could give AI a massive boost, helping it search through ridiculously complex problems. And there's the flip side. That same power could potentially crack the encryption that keeps all of our online data safe right now.
But here's the tough reality check. Qubits are unbelievably sensitive. Like the slightest vibration, a tiny change in temperature, even a stray magnetic field can knock them out of their quantum state. This interference is called noise, and it's the biggest enemy because it causes errors. Look at this chart. It's from a simple quantum test. The ideal result is 1024, but the actual result on a real machine, 765. That gap, that's all errors caused by noise.
So building these things is an insane engineering challenge. We're talking about shielding them perfectly and cooling them down to temperatures colder than outer space. We are truly at the very beginning of this quantum journey. And so the real question isn't just, can we build them? We're getting there. The bigger question is, how are we going to control these incredibly powerful yet incredibly fragile machines to make sure they actually change the world for the better?